Thanks for attending. Thanks for taking your valuable time and spending it here today talking about domain-driven design. What is this whole thing about reactive DDD? So let's just discuss that for a moment to kind of set the stage. So we're talking about domain-driven design, but we're also using domain-driven design in what is contemporarily been referred to as reactive systems or reactive programming. And this is where everything, pretty much everything in the system is asynchronous. Now, even the term asynchronous can be a little bit confusing term or disputed. What is asynchronous? Well, let me define asynchronous, and I'll define concurrency, and I'll define also parallelism in the form that I'm talking about. You may think of it a little bit differently, but this is sort of the framing that I'm putting with it. So asynchronous is where things happen and they appear to happen concurrently, but they may not really be happening concurrently, because you can do asynchronous processing with a single thread. Okay? And this is where you just simply give a little slice to, could I get the volume down a little bit? We're really echoing. Yeah. Okay. I think that's better. So the asynchronous can have a single thread where perhaps you have a cooperative component or a set of cooperative components that do some processing, and then they give up the thread for another component to use. Think of, how many here remember Windows, like Windows, native Windows programming, like 3.1? What is it? Yes, Charles Petzold book. So that was asynchronous, but it was really running on a single thread because there were no threads in Windows 3.1. It was simply just one processor, like a 286, maybe 386 processor in those days. It's hard to remember exactly, but so what would happen is you would have an event loop, right? And this event loop would process events as they happen. And so you have maybe 4 or 5 different windows on the screen, and events are happening in various windows. And so by processing through an event loop, you allow the Windows kernel, if you will, at the time, to basically take various events or messages that are happening and distribute them one at a time through the event loop, and those would be dispatched through the event loop to the various windows. Okay? And so that's asynchronous. When you looked at the desktop, many times you had a very good sort of perception that things were running in parallel. But then there was always, the clock up in the corner, and you would see the clock hand sort of pause for a few seconds, and then it would jump forward. So you kind of knew that the asynchronous nature of this environment wasn't perfect because it wasn't really doing things concurrently or in parallel. Okay. I think you've got that. What is concurrency? Concurrency is where you have at least 2 threads available, but you may have even more small processes that need to be run. And so basically what happens is, let's say that you have 10 little jobs or processes that need to be run on these 2 threads, and those 10 processes will sort of be distributed across the 2 threads. So you can imagine 5 of these little processes waiting in line to get a slice of the thread, right? So that's one way to think about concurrency. And of course you can have any number of those mini processes lined up, and they could be lined up across even more threads, but it means that there are less threads or cores than there are processes, so you have to share. And then there's parallelism. And parallelism is where, I mean, it's really, borderline concurrency, because you'll have, many more cores or threads available to run, but it's quite likely that as you start to take advantage of this, even though you would hope that let's say you have an 8-core, like this is an 8-core machine, this 3-year-old Mac, and I would like to think that every single little piece of work that I need to do is running in parallel, but the 8 things, the 8 little processes that are scheduled right now, and the dispatcher dispatches those, are running on a thread right now. So those operations are running in parallel, but again, it could be that we have, thousands, tens of thousands, maybe even millions of tasks waiting to have a slice of that. So parallelism is where things all happen at the same time, but again, parallelism may be sort of, may fall back into a concurrency environment. So that's what I'm talking about with concurrency. Now, reactive means that you are reacting to all these things that are happening, and the only reason that a component is running at any given moment is because it is reacting to something that happened, okay? But we're framing all this in the DDD way of expressing software, which is fluent. It's also linguistic because it is fluent. And now what happens? Well, I'm going to show you how uncertainty creeps in to these kinds of environments. And you probably already have, an idea going on in your head, if you're not already familiar with this topic, that, wow, as 100,000 things happen sort of very close in timing to one another, how do we order all these things and make them, allow ourselves to reason about the complexity of this? Okay, so let's talk first about DDD specifically. I would say that a lot of people think that they know the definition of domain-driven design. It means different things to different people. To some people, it might mean the aggregate pattern and using domain services and repositories. Maybe that's what DDD means to you. I've spoken to many who say, yes, I've been using DDD for 2 years, and I ask, how have you used it? And the explanation is generally very tactical, right? It's the fine-grained components that they're using. But that's not in essence what DDD is about. DDD is in essence about this. It's about a bounded context, and I'll explain that in a moment, with an explicit model that reflects, or you might say models, a ubiquitous language. Okay, wow, there are a lot of terms right there, right? And you're like, okay, man, bounded context. Okay, let's just break this down very simply. A bounded context is just a boundary around some software. Just think about saying that these specific components, like you see 3 here, they belong together. And so we're going to draw a boundary around that, and we're going to say that these belong in that context and others do not. That is essentially what the bounded context means. But the bounded context is linguistically inspired and driven. So it's the job of a team as they are, going through the fairly complex process of uncovering a lot of details about their model. They always walk into this new project with some ideas of how it should work, right? And that's basically recognizing the known knowns. Okay, so you walk in and you take a look at or have some conversations with people, and the easy stuff just always floats up from the beginning. But but there are also, as you're having these conversations, you're realizing that there are some known unknowns about your exploration. And as you start to discuss, you're collecting more in your mind or maybe taking notes and saying, okay, well, saying that or describing that part of the model implies that we need more understanding about this over here, some sort of supporting component or concept. But where DDD really pays off is when you explore far enough and you learn enough about the model that you finally uncover the unknown unknowns, right? Where you didn't know, you had no idea that there were some sort of concepts that were lurking in there in this model. And it's a unique experience too, because any given team could uncover different ones, right? Because it's all the process of learning together as a team, and as you go through that learning process, you are experiencing the discovery of things. You might call them breakthroughs, okay? Hopefully they are breakthroughs, because that's where the real value comes in with domain-driven design. And that's also why you probably shouldn't use the most parts of domain-driven design in every project, because some projects, some models are just not worth that effort. Therefore, domain-driven design focuses on what is known as a core domain. A core domain is what has the potential to uniquely distinguish the organization that's building this software from all others who may be competing with them. Okay? Okay, so we're making these discoveries, and we have an idea that, wow, look at this, that, and we come to an understanding. What do we naturally do? We name the concepts, and we have descriptions for the behaviors of those concepts. Now, I'm going to make a point in a few moments about the importance of not neglecting the behaviors, because as software developers, are we all software developers here, by the way? Everybody? Okay. Any business, more like business stakeholders here? Okay. So you know what, you're going to agree, hopefully, with what I say. We're so obsessed with the nouns, right? I mean, everything is a noun. And what happens because of that is we just think about setting data on the nouns. And the nouns become all important, but we miss the behaviors. I'll come back to that. But because you are having these discussions not only about nouns, but the actual sentences that describe this modeling process, well, you're going to come up with sentences that have verbs and adjectives, and these kinds of things will help you to form an entire vision of a model that will then be realized through implementing it in code. And it's linguistically based because this particular boundary says within this boundary, we are speaking this language. It is a domain-specific language about this core model, which means that the concepts that we use have a specific meaning and definition in our context, and they have specific behaviors. But if that same concept is recognized in another boundary, it very likely has a different definition, whether a slightly different definition or vastly different. It will have a different definition and different behaviors and even different data associated with it than the concepts that we have in our model. And this is very unique about domain-driven design because it's important that we make that mental separation. How many here have ever tried to work with a canonical data model? How did that work out for you? So, right? So one definition for every single concept through the enterprise, right? So we have 25 different definitions of product. So we're going to try to support all 25 of those definitions in one nice, tidy, 50,000 line class. It doesn't work out so well. Okay, so that sort of gives you the idea of if you say that you are practicing domain-driven design, that is primarily what you are working on. Okay? And now, because we have a context boundary around the core, and pick any one of these ellipses, and they're going to be, a core. One of them will be a core, and let's say the other three are supporting or generic. Okay, so domain-driven design is not only strategically valuable for identifying what is core, as in what will make us more successful in competing in the marketplace, but it's also important for recognizing what is not core. So we're actually going to make a decision not to invest in some bounded contexts in exact opposite of the reasons that we are going to invest in a certain bounded context, okay? So you'll have certain software that you could buy off the shelf. That's a generic subdomain. And I don't mean the library necessarily, but some model that you can purchase somewhere. But you purchase it because it's not going to define what your company is and what they do. There's going to be some other software that doesn't exist, and it's absolutely necessary to implement. You can't buy it anywhere, but you also don't want to invest heavily in it as you would a core, and so that's known more as a supporting subdomain. Okay? So you have all these bounded contexts, and now we have to understand, okay, we've broken up all these, what we could build in a monolith, and instead we've broken them apart and recognized the different linguistic influences on each different bounded context. But now, how do we make them work as a whole system? Right? That is what context mapping is about. So I talk about this bounded context in one team, and I talk about this bounded context in another team. And when we recognize that we need something from them and or they need something from us, then it's this line that is the mapping between those two context boundaries. Okay? How do we exchange the data? What kind of boundary APIs are available to it? Is it REST? Is it SOAP? Is it ad hoc queries against their database? Do we actually have foreign keys across schemas, across schema foreign keys, and well, when you get into that, you're probably not even talking about a nice green boundary. You're talking about a very muddy, gooey boundary that we referred to as a big ball of mud, which is a monolith and worse, right? It's everything that could possibly be wrong, or pretty much with a system in terms of, if we're talking about clean design, it just pretty much doesn't exist. But these systems make money, right? They're around. They're still around from 25 years ago, and they still use btrieve, databases because, when was that? The mid 80s or something? Early 80s, btrieve. They still use those because they make money, but they're getting really slow. You can't even upgrade the technology any longer, and there are all kinds of problems with them, and probably the very worst problem is they're difficult to change. And so you end up slowing down the team's cadence in order to make sure that nothing breaks when they make this one, what appears to be a minor change. Nothing breaks here, and nothing breaks clear across the enterprise, because who knows what's dependent on that. Okay, so we need context mapping, and each one of these lines represents a different kind of relationship that could occur between the teams and the boundaries themselves, the software that's in between the line. Okay, so you have to think about that, and recognizing the boundary, the relationship between the two boundaries is extremely important, because if you think, for example, that your team is in a partnership with this team, but you're really in a customer-supplier relationship, you're in a lot of trouble, because you think that you're going to be able to ask this team to do something immediately, and you think they're going to say, it'll be there tomorrow, but instead they're going to say, we can't get to that for a few months. Okay, and those kind of, walking into that situation without a clear understanding of your boundaries could be detrimental to your project. So those are two, I would say, for me, really, the most important things about domain-driven design. Now we choose a language that we're going to implement with, and we choose some technology, beyond the language. So are we going to use object-oriented? Will we use Java? Will we use C#? Ruby, go on and on. And will we use Oracle database, or will we use some sort of NoSQL store? Where do we go from here? Well, those are all important choices to make, and there are probably some architects here that their eyes would start twitching. I've had conversations with, interestingly enough, I ran into George Fairbanks today, and I'm like, George, and George inspired me to write chapter 4 of my red book, Implementing Domain-Driven Design, because George kind of, challenged the whole DDD idea architecturally, and so I wrote this very detailed chapter about how many different architectural influences and styles and patterns you can use to support DDD. And that's actually one of the most popular chapters. So some people might call what I just said as emergent architecture. I don't think that's true. But we choose the right architectural components for what we need. We don't first choose our components and then decide what software we're going to build around it, right? That's I think, also a very DDD way of thinking. And here's some other things to look out for. I like the sort of Batman, approach to this, because we don't want any of this negative influence in our models. Probably first and foremost, modeling without domain experts. If someone says that they're using domain-driven design, ask them for the name of their domain expert or experts. If you hear a pause, they're not doing domain-driven design. Okay? Well, domain-driven design is about the domain, it's about the business, and programmers don't get the business out of just reading some requirements documents that are hand-me-downs from the real expert, and maybe they've passed through at least one other desktop, if not multiple desktops, and refined and whatever, and everybody squeezes their opinion into this use case or whatever it is, and all these opinions then go to the programmers and they interpret it as entities and value objects and repositories and whatever. But what you get, as the country saying goes, may not be a 50-second cousin to what the domain expert really wanted, okay? So it's not just programmers. You have to work with domain experts. Anemic domain model. Okay, I'm getting back to this topic where we only think about the nouns in the model. Whatever the nouns are, product, catalog, invoice, shopping cart, whatever. And so what we do is we think about these nouns. We don't think much about them really. We just sort of have a gut feeling for what they should be, and we slam them out because we think it's easy to do that, and then we just start pushing data into them, right? And then we save them in a database of some kind, and we ship. Well, that's not what DDD is about. DDD is about operations. Those operations may be immutable or side effect free operations like we would use with functional programming, or value objects in an object-oriented environment. So basically where we try to keep each part of the data in the system as completely immutable, and we may replace some data, but we don't change that exact data. Or it could be a matter of operations on an object that affect the change of state in the object. In whichever case you choose to use, behaviors are what cause those pieces of data to change. And the behaviors, the operations, the functions, the methods, whatever you like to refer to those as, should be fluent. They should capture the ideas behind domain-driven design, behind the domain model that you're working in, and the domain expert that you're working with, and the team's refinement of those ideas. Another thing that you really need to be explicit about is the data types in your model. And this can be tricky because you think that, I've named a product, and I've named a catalog, and I've named an invoice. We're good. Not so much, because when you look inside that product, is its product identity literally a Java UUID or a .NET GUID? Is it just a long? Is it just a string? Well, you have to consider, at some point, when is it helpful to have a strongly typed concept around what may seem to be a minor piece of data? Now, who here has used big decimal for math problems in their domain? Okay, one. Two. Can either one of you just say right away what's a huge problem with big decimal? I mean, it solves some problems, but just think about passing a big decimal around. What happens? Okay. So precision is extremely important, and yes, so they can lose track of, well, is it a currency right now, or is it is it just a whatever, something else? And what happens when you multiply and divide on a big decimal? What do you have to do? You have to choose your precision, your decimal precision. And if you don't have that decision captured somewhere in your model, all kinds of things can happen to it as it goes around as a big decimal, around different pieces of data. So that's where, for example, a big decimal would be much better wrapped in a money type, if we're talking monetary values. And we have all the rounding decisions in the money. And so when we want to multiply, divide, or add or subtract, or whatever kind of operation we do, we add monies to monies. We divide monies by monies. We multiply monies by monies. And internally, the operations are sound and the rounding is sound. And what do we get back? Another money. Okay? That's a value object. And we can do the same thing with identities. Okay? Domain-driven design is not about the persistence in messaging. I hate to kind of say this, but I attend conferences and talks and everything where people are using domain-driven design, and what people like to see is live coding of DDD. It just doesn't make sense. I have to say it. Okay, you got a couple people, pairing on a refactoring. That's acceptable. But you got two programmers up on the, at the lectern, and one is just spewing stuff about his opinion about stuff, and the other one is just coding at 1,000,000 miles a second. And their focus is also quite generally on persistence in messaging. They're talking about a specific database a lot, and they're talking about what? Kafka a lot, right? I mean, if you're not saying Kafka almost every other sentence, you're just, it doesn't work. So really what you need to do is consider, what is our model about? What kind of SLAs do we need? What would support that, And if you're processing a total of, a few million messages per day, even if you are using Kafka, I just don't think you need 36 partitions. So, think about that. Now, this statement, I like to say this statement because it's very pointed. You are not Google, Netflix, or Amazon unless you are Google, Netflix, or Amazon. So just consider that this statement doesn't say that if you are working at one of these places with huge, throughput, low latency, high scalability, that you're not them. Well, you are, but don't try to be them just because you think it's cool. Just choose the right mechanisms for the job. All right, so I'm just going to walk you through a reactive platform that I'm working on right now. It's called Vlingo. It's open source. So you can go to github.com/Vlingo and download this platform right now. It's in early stages, I have to admit, but what is out there is fairly solid, and I'm still building components on it, and I'm getting some help with it as well. So I'm just going to walk you through what makes a reactive platform, and what makes a reactive platform great to use, and what makes a reactive platform, blow your mind at the same time, okay? And that's what I'm talking about, dealing with uncertainty. Now, this presentation has a little bit of a mishmash of diagrams in it because these are just newly designed diagrams that I'm showing, and we're kind of changing our look and so forth, but I just thought I would introduce these ideas with these diagrams, but then I'll fall back to my kind of, I guess, legacy or heritage diagrams too. So this is what we're all used to, pretty much, right? When the very first program that you ever wrote, and you learned how to call a function or invoke a method or, something, you think back to that moment, and you're like, wow, this is super cool. And you know what part of the real coolness was? Is that you didn't have to worry that the whole world would change out from under you before you got a response from the method that you invoked, right? Because you were blocking. You were doing nothing, and this, by the way, is a client object in a VM, and that's a server object in a VM. We're not talking about remote, request response. We're talking about a blocking method invocation on two objects. And we become very comfortable with that. And it worked out great while Moore's Law was still applicable. Now, Moore's Law was, I'll show you a diagram in a moment, but it was like shh, right? But now it's even like shh. Why? Meltdown inspector, right? So, our processors are slower now than they were, what was that, 3-4 months ago when that discovery was announced? And as it was, to see the kinds of processor gains that we were getting through the, let's say, 80s, 90s, early 2000s, up to maybe 2003, to see those kinds of gains today, which were happening in a year and a half or 2 years, takes about 9 to 10 years now, even without considering the impact of Spectre and Meltdown. So blocking is not as friendly to us as it used to be, right? We could always count on processors making up for the lack of speed in our software within a relatively short period of time. Okay, so we introduce actor model now. Who here is familiar with Alan Kay? Oh man. Okay, go look up Alan Kay. He's the inventor of object-oriented, basically. Okay, there was Simula before there was Smalltalk, and I'm not going to try to say that I know Simula, but it had, I guess, a few object ideas in it. But even, Alan Kay talks about the influences of different systems and languages that he worked with that had an influence on his thinking about object orientation. But what Alan Kay is very explicit about today is that he is basically not happy with the way OO turned out. And let's not even talk about Java and C#. I mean, he thinks those languages are abysmal. And maybe, any one of us agrees with that. But Alan Kay's point is that even Smalltalk didn't turn out the way that he wanted it to. And if Alan Kay would have had his way with Smalltalk, as its inventor and object-oriented, he would have had things much more asynchronous. For example, he taught kids how to do Smalltalk programming with the actor model, and little children were programming against 200 threads, running threads at one time. And so when someone says that, parallelism is hard, Alan Kay would go, oh yeah, I taught kids to do that, Well, that's how OO would have turned out if Alan Kay would have gotten his wish, so to speak, or what he was determined to do. So he says that the actor model retains most of what he thought were the good ideas about objects. And one of those is that each actor is its own sort of little universe. We can call it a little computer. We can call it, some kind of world or whatever, because, it has this idea of encapsulation, but it's also very message-driven. Okay, and that's what we're looking at now, is instead of invoking a method from a sender onto a receiver, the sender sends a message asynchronously. Let's just say asynchronously, because it may be concurrent, it may be parallel, but that is not important. The important part of it is that this sender doesn't block, waiting for the receiver to do something. If we only have one single thread in the whole system, this sender will continue to process. As soon as it sends the message, it will continue to process, and that receiver is entirely dormant until that sender relinquishes the use of the thread, and then the dispatcher will schedule this receiver to use that thread. Now, you can extrapolate that from the into the concurrent or parallel model, and I think you get the idea. It's just a matter of the number of threads that makes the difference. Okay? But actors are message-driven. Okay, the Vlingo platform is a number of components. I'll just mention a few here, and then I'll introduce you to some of them very quickly. There's an authorization service for authentication and authorization. There's a directory service, which is service registry and discovery. And then there's some more, application or service-centric things like Vlingo Streams, which is both streams for streaming over messages or events or whatever it happens to be, and also it supports event sourcing, and I'll introduce you to what event sourcing is here in a few minutes. And then Lattice is that thing that sort of runs across many nodes, and I can just send a message to any actor anywhere, and it'll just end up being dispatched to that specific actor, and I don't have to understand how it works or anything. And you're thinking, oh no, distributed objects. Okay, it's not the same. And it works quite well, and there's the obvious efficiency that if one message is sent within a single VM, there's a huge performance gain in that. Okay, so Vlingo Actors is sort of the bedrock of the Vlingo platform, and it's so easy to use. You basically have a controller or some sort of, for example, resource handler, and that resource handler gets some sort of, let's say, REST request, and it can directly dispatch to another actor, which is a DDD aggregate. Okay, and an aggregate is basically a special kind of entity. And because this aggregate has a mailbox, and it's already received command 0, which it's processing right now, and it has emitted an event, and that event is emitted asynchronously, and it's going into persistent storage in an event store. But this actor is not locking anything internally. There's no blocking, there's no volatile anything in there, because the actor is only handling one command at a time, which means that as this controller sends command 4 to this aggregate, it's going to go into its mailbox behind the other commands that are already there, and they will be processed in the order in which they were received. Now, you might think to yourself, well, that's not really concurrency, but all I can say is, well, yes it is, because while this one actor is handling only one message at a time, there could be millions of other actors processing the same kinds of commands or any other kind of message, in essence, simultaneously, because depending on the number of cores and the number of available threads, obviously, there's task switching going on constantly, right? So, although any one actor is nowhere near as fast as a single client invoking a single method on a server object, right? It just can't be that fast. But overall, the entire system is plowing ahead faster because there's no blocking. There's no locking. Not even at the database level. And there are some tricks around that, but that's the whole idea. Okay? Of course, we have clustering, so this shows a 3-node cluster, and the cluster has, a quorum calculation that it goes through. If a node is lost, do we still have a quorum of of the nodes that we need to, basically total nodes divided by 2 plus 1 is the calculation. And if we lose one node, we still have a quorum. If we lose 2 nodes, in this case, we don't have a quorum. And let's say this is the one remaining node, it will go into a idle state until one of these other nodes is reactivated, restarted or whatever, and then it can go active again. And there are different strategies that you can use with clusters. Okay, REST endpoints. This is Vlingo HTTP. So this is an HTTP server that is extremely fast. I regularly test sending, so request and response, 10,000 requests, 10,000 responses in about 700 milliseconds, okay? Which is, what is that? Is that about, well, if I do 100,000, so it's about 70 nanoseconds per round trip, right? That's, so if you're wondering if actor model is fast, I think that answers the question. So directory is, services register with the directory, and the directory sends out broadcasts that says, okay, here's all the services I know about, and then if any of these need to talk to those services, they know how to talk to each other. It could be through REST, or it could be that I need to discover where some streaming service is so that I can get its events or other messages that are being streamed. And the auth is basically authentication and authorization. You understand what that is, but it allows the directory, for example, and streams to make certain that any service that's trying to read a stream has the permission to read the stream, and it has permission to read any given kind of event or even any piece of data within the event, which is really good for European privacy laws right now, or regulations. Okay, so now you've kind of got this snapshot of DDD and what reactive is. Okay, what does this represent? Powers of 10. Did you ever go to see that IMAX film? That's sort of like, I don't even, but they zoom in and out on things, powers of 10. And you may be looking at like a power of 10, zoom in on a blade of grass or an insect, and then you zoom way out and you're powers of 10 into the universe, into the galaxy, and you're looking at stars being born. And to some extent, you can't tell where you are at any given point. Literally, you're looking at it and you're like, okay, am I looking at that blade of grass or the insect or a star being born? Well, that's a little bit what reactive is like, right? There's so many things going on simultaneously that trying to sort of reason about the whole system all at once can become quite mind-boggling. But if we think about any one of these individual dots on here, whether this is a galaxy or whether we're peering inside of an atom, we can reason about the messages between any two of those objects, or only to the point where the object / actor is receiving some kind of stimulus, a message, and it is emitting some kind of result or outcome. Okay, so don't get overwhelmed by this. And another thing too that we have to understand is, I think everybody's familiar with this statement by Donald Knuth, and everybody misquotes Donald Knuth as saying this. Do you know that Donald Knuth, he said this, sort of, but he didn't say exactly this. So everybody's sort of condensed this, and it's become an excuse not to think about any kind of optimization, right? Yagni, you're not going to need it. Premature optimization is the root of all evil. Now, let me show you the exact quote. Forget about small inefficiencies. Premature optimization is the root of all evil. having a single thread for a single app, and even that thread is only available while the OS isn't using it, right? Having that single thread is the root of all evil these days, because computers don't work this way anymore. There's an article on the ACM, recent article. It asserts that C and C++ are no longer low-level languages. And your computer is not just a fast PDP-11. Does that make sense? Do you know where this is headed? The C programming language was written for the PDP-11. I never used a PDP-11, but I did use a VAX 11780 on Unix with C, right? And then I did a lot of programming in DOS and OS2, Windows and what have you, and Unix, and in a micro setting. But all of those microprocessor architectures were pretty similar, right? Up until the point where cores didn't get, or processors didn't get any faster. Now what? We have to completely re-architect the chips. And how do we re-architect them? We give them multiple cores. But here's the catch. We need to make C and C++ programmers believe that they are still using a low-level language and an optimized language for this new architecture. And so what do? We allow the processor to guess what it thinks that C program is going to do next. And when it's wrong, it has to clear that, which gives the opportunity for an attack on the processor. So quite literally, the point of this article is that Intel and other processor engineers, in trying to make this processor, these new processor architectures, still look like they're a reasonable source for a C program to run on, has caused these vulnerabilities in the processors. And to boot, C and C++ don't perform that way anymore. It's all fake. Something else that Donald Knuth said. Anybody that has more than a casual interest in computers should have at least some idea of the underlying hardware, or what the underlying hardware is like. Otherwise, their programs will be pretty weird. Now, what does that say about C and C++, right? Now, I have probably at least, a combined 20 years of experience with C and C++. So I'm not, just dogging the languages, but there are better languages now for this, and there are better ways of processing data. And actor model is one of those that takes advantage of the current hardware architectures that are being shipped. So know about the hardware architectures that are available and use the right tools for those architectures. So this is what I was talking about. Back in 1973, right? Moore's Law. The meteoric rise of processor speeds. And then about 2003, right? And now, if you project this out here another 10 years, you'll see the kind of growth that happened from here to here, right? Or even less, right? So that's what we're facing. Now, why do I choose the year 1973? That's the year that Carl Hewitt and his associates discovered or developed or invented the actor model. Now, think about Carl Hewitt inventing the actor model back here. This is a person with vision, because Carl Hewitt did not have, generally speaking, the kind, or at least not the industry as a whole, did not have the kinds of processors and fast networks and distribution that we have today, which is really But Carl Hewitt said, I'm doing this because I know it's going to happen, even though it took like 30 years, right, for it to happen. So cores matter. Cores are not getting faster or much faster. We're getting more cores, though. Reactive is important. So instead of using a thread all the time, any given component only uses a thread when it has something to do. Otherwise, it's just out of the way. Don't have to worry about it's not using the machine. Reactive systems then, this is like, take that power of 10 slide with some kind of stars or atoms there, and now we're looking at sort of the minutia at the object level, and here we're looking at the system level, and it's still reactive. Because events that are being emitted from this service, bounded context, are going into some topic, and the topic is being subscribed to by other microservices, right? Okay, now we get to the, we reach the cusp of the matter, and that is welcome uncertainty, because this is how we like to think. We want to believe that when I put event 1 into some persistent stored durable queue, and I put event 2 in after it, and I put event 3 in after it, that some other service or my own service is going to see those as in the same order, event 1, event 2, event 3. You know what? I already mentioned the popularity of Kafka, and Kafka is a great tool, but they're trying to convince people that they have exactly once delivery. It's just not possible. After you get by all the sales material and you really ask the question, the answer is, well, sometimes. Well, sometimes means that you got to plan for it 100% of the time. Because if sometime ever happens, and it will, it's going to catch you by surprise, and you won't know when it's coming. That's the worst kind of mechanism to use, is where you think you're protected, but you're really not. Okay, uncertainty. I found this really cool definition for uncertainty in the dictionary. It's the state of being uncertain. But I know, this is a popular slide, but you know what it is? It's a state, right? It is a state. Uncertainty is a state. And that's where we're going from here. I want you to focus in on the fact that uncertainty is a state. It is a current state. We don't know what's going to happen when, but we can model around that problem and make it not only possible to reason about, but actually simple to reason about. And you're thinking, come on, no way. And what I'm going to do is I'm going to show you that the climax to this whole talk is going to be very anticlimactic, because I'm going to show you how easy it is to think about this stuff, and everybody just for some reason tries to make it difficult. And I'm going to show you why it's not. So, so this is what uncertainty means to us. It's unpredictable, it's unreliable, it's risky, it's happening by chance, it's precarious, it's changeability, it's variability, and okay, it all boils down to this, right? Uncomfortable. We're all uncomfortable. And you know what uncomfortable means is we don't like it. But we have to actually get used to being uncomfortable. It's not that bad, as I'm going to show you. So, again, we want blocking. We want to think, okay, the world stops here until that other thing happens, and then I get some idea of what happened, right? And we have this addiction of order, pure order. And we have this addiction of ACID transactions. Okay, I need to change 3 different databases. They're all changing in the same transaction, right? XA, global, transactions, whatever you like to call it. It's okay. Don't worry about what used to be. In the distributed model that we are, by and large, using today, it just doesn't exist, right? Now, Is anyone good at sort of visualizing audio stereograms? That's what this is. You see what's there? You see it. Usually, I was giving this talk in Oslo last month, and they were like, I want the beer you're drinking, you know, because they couldn't see what is it? You see it, I think. It's a shark. Do you see the shark? There's a shark in there. Really is. You kind of have, I mean, I've seen it, but right at this moment, I probably won't be able to, but it's there, and he confirmed it. And it's sort of like the nose is about right here, and the tail is like up about here, right? Is that true? Yeah. And, okay, it's a matter of perception. So if I stand back and I squint and sort of cross one of my eyes a little bit, and some people, I don't know why it jumps out to some people, but it does. And others, it's just like, you can look all day and go like, ah, you know, it's like, I want to see this, and you can't. You know what that's very much like is this. The cores in this processor, right? I mean, look carefully. They're hidden in there, but you can find them if you have the right tools. So, you know, learn to squint and cross your eye. You need to learn about these. Fortress. What is this fortress thing about? Well, what happens is when we're working in an uncertain environment, what do we try to do, right? We try to make everything certain. Instead of embracing the uncertainty and saying things happen completely out of order and there's chaos going on, instead of accepting that and saying, okay, let's learn to deal with that, we say, no, no, no. What we're going to do is emulate certainty in an uncertain world. How do we do that? We put mechanisms, like this is called a ports and adapters architecture. Maybe some of you are familiar with it. It's also known as hexagonal or hexagonal or onion architecture. It's just different names for basically saying we have some ports on the outside of our service. Those may be HTTP ports or you know, AMQP ports or whatever. And when something enters, we adapt what enters to something that the inside can deal with this. And this is our domain model here, and these are just some application sort of orchestration services around it, right? But what I'm pointing at here is that when this event, this is an event because it's orange and it has a lightning bolt, you can tell it's an event. And this event enters, and we have two mechanisms here. One is made to make sure that we don't have any duplicates, and the other one is made to create total order. Do you know what the patterns are called? They're in Gregor Hope's book. Deduplicator and resequencer. You've probably read about them, maybe even used them, okay? Deduplicator. So, you know, that, like they say, there's only one hard problem in software. That's complete order of messages and exactly once delivery and exactly once delivery and, right? So, event 1 arrives, event 2 arrives, event 1 arrives again. How is that even possible? You know how it's possible? Just one simple scenario is that this mechanism didn't acknowledge event 1 quickly enough for the messaging mechanism to not send another one. But that's a good thing. We actually want at least once delivery from those kinds of mechanisms. If you don't have at least once delivery, a la someone tries to sell you exactly once delivery and you buy it, right? And then it bites you. But if you're doing this stuff really, the safest way is you embrace at least once delivery, and you say this might happen multiple times, right? And then there's the resequencer, okay? Event 3 arrives, and it can happen for the same reason, things happen out of order, threads, right? Distribute your processing in a parallel way across multiple actors. Which one finishes first? I don't know. But do we have to sequence everything for everyone? No. We just simply emit the event that causes it, and now event 3 shows up before event 1, and then event 4 shows up, and then there's latency, maybe minutes, and finally event 2 shows up, right? And this is what we want on the other side. We want complete exact order. 1, 2, 3, 4. Oh, feels so good, right? So we write a resequencer. And what we're really doing, though, is we're telling the service, you can't do any of this other stuff until we see every bit of it. That's a very high potential for a timeout situation when it's completely unnecessary. You know what else is true about these mechanisms? They're hard to implement. Okay, no, it's not difficult to save an idea of some kind in a database and look back at it later and see, have we already seen this? Yeah, we have. Throw it away. You know what's hard is? Decide when it's okay to delete that look-back record in your database to deduplicate with. Is it okay to delete it after 24 hours? 48? Keep going. 7 days, is that okay? Go ahead, delete it. 1 hour after you delete it. Uncertainty, right? So this is hard, and you haven't solved any business problems yet, right? So instead, why don't we just, instead of trying to stop everything and make it all, line up to the way that we've been taught to think, why not simply realize that distributed computing is a thing? It's what we use these days. So model around it. Model for distributed computing. So we want to say, stop everything. Okay, I'm ready now, right? This fella, Justin, says there is no now, right? And I'm going to show you why. There's a global bug lurking everywhere. Datetime now is a lie, right? As soon as you get the answer from datetime.now, it's wrong. Same with local time. So C# or Java, either one, it's wrong as soon as you get it. Right? So look, just accept the fact that we're dealing with uncertainty. And so, I made this up and everybody loved it. I don't know why. But I said, if you don't like distributed computing, it's here to stay. If you don't like it, change careers. Maybe start a restaurant. But you know what? You're still going to use distributed systems in the restaurant. You may not be writing them, but you'll use them. Some people think there's a lot more risk in the restaurant business than there is in technology, too. So, so why don't we just learn to deal with it? How do we model uncertainty? Okay, cores matter, the cloud matters, all of these things, microservices are happening. Some companies have so many microservices, and I'm talking about the 100-line variety, that they don't even know which ones they can stop. Which ones are now obsolete? Let's take it offline. They don't know if they can do that safely, so they leave them all running. You know what that definition of that is? Distributed monolith. Right? When you do not understand what is going on, and so you just leave things running because, it only costs $400 a month per service, seriously, why don't we talk that company into understanding their software and donating the money they save to some starving country, right? So, latency matters. The network is real. We use it all the time. IoT matters. All these things are cheap. We're not going to escape them. Okay, so we're going to deal with uncertainty. Now I want to go back to the business side of things. we put so much effort into designing classes that are just pristine and perfect, right? That's what solid helps us to do. We walk down the line. Single responsibility, open close, Liskov substitution, go on, right? And so we obey all that, and we have classes that don't work for the business. They look beautiful, hundreds of them, and they don't work for the business. Do you know what ma is? I had someone in Oslo who speaks Japanese, and he raised his hand right away. Ma, I know what ma is. Ma is rough. Do you know what ma is? It's Japanese, but I know, are you Chinese? Yes, but sometimes you know Japanese, I don't know. But ma means the space between in Japanese. It just means the space between. And Alan Kay says the ma is more important than the inside of the object, right? We contort and refactor and, oh, look at this beautiful class I have. And you know what? The messages or the invocations that we pass in between make no sense to anyone. Even the programmers who walk in behind us have no idea what setting 25 properties means in this service, you know, and you look at this and it's like, what is that doing? You know, oh. So what Alan Kay says is, what's most important are the objects and how they are identified themselves, the actors. How do we name them, and how do we name the messages that we pass between them? Don't put so much emphasis on the inside design, put more emphasis on the outside design, and this is very DDD. This is a very DDD approach. So we want to create reactive systems in an uncertain world. Pat Helland, you know who Pat Helland is? He helped make Amazon what it is with, you know, uncertainty everywhere. And Pat Helland in this paper, it's now on the ACM, I believe, it's Life Beyond Distributed Transactions. It's an updated paper from one that he wrote like 10 or more years ago. And he said, in a system that cannot count on distributed transactions, the management of uncertainty must be implemented in where? The business logic, right? Totally throw out those resequencers, the deduplicators. Let's make this easy. And we're solving business problems. So Pat Helland said, we're going to deal with this as activities. And he just threw this out as an idea. So I'm not criticizing it, but this is sort of the, in Pat Helland's, you know, paper, he talks about partners, as in this entity and this entity do things to work together. And they send messages to each other. And as they send messages to each other, they need to track what has already happened. And we're going to do that through a partner activity. Each one of those behaviors that happen between. And when I read Pat Helland's paper, this is sort of what I see, right? I see this set of individual activities that have happened, and then I see the opportunity to record a new activity from a partner and the activity itself. And so I'm just going to save that in this partner activity set. And then I can also ask, have I seen this partner activity before? And if I've seen it already, then I know I don't need to act on it in some way. Now, the problem with this is it's the same for everyone. But we haven't solved any real business problems. We're still doing sort of, you know, an artifice for the technology. So let's look at how we could do this in the domain model. So we've got these events and commands flying around everywhere, but we've got these concepts. We have the concepts of a pricing calculator, a pricing range or a price range, a proposal, and a job. So this is describing a B2B, a P2P economy, so a peer-to-peer economy where people are looking for other people to do jobs for them. Someone submits a proposal, I need this job done. Some workers are going to react to that and do something, and hopefully they'll get the job. But we also have a pricing calculator to make sure that everything is fair. So this is kind of the domain, and you might look at the matching part of this, and I drew it big so that you would think that it was the most important. But when you think about it, in this day and age, you know, matching, when you think about just the sort of that handshake that's going on between a client and a worker to do some job, right, propose, that's just kind of a website. I mean, there's a little complexity there, but the real complexity is in the pricing, right? This is where we have to gather all kinds of data about what is fair pricing in this particular piece of work that needs to be done, you know, so we need probably some kind of taxonomy and you know, and we need all kinds of ongoing analytics running. Pricing is probably core, right? So pricing is going to see events from matching that says, I just have a proposal that was submitted. And that proposal submitted will also be seen by scheduling, and scheduling does some heavy lifting too to try to figure out who's available to do this work, who has the skills, and who has the time. So what happens if we receive duplicate messages of some kind, whether they're commands or events? If they are commutative operations, it's simple. Just decide, is this operation that I'm handling right now commutative? What is commutative? You probably remember that 2 plus 3 is 5, and 5 plus 3 is 2, right? It doesn't matter how many times you add those two numbers together, they're always the same. So you simply have a state with a value, and no matter what order these things come in or how many we see, right? We set a state and we can look back at the same state and simply say, seen it before. When that state originally transitions, we want to emit an event. But what happens if we emit that event every single time that a duplicate is seen? Well, at best case, it's just completely inaccurate. It could cause problems for other systems or other subsystems. Non-commutative, though, is where you have to keep some sort of unique identity. But notice that you're keeping that unique identity in the domain object itself, represented as an actor, as an entity actor, but we have some kind of unique identity that says, we have seen this before, but it's right in the model. It's not out at the edge. So we're persisting these objects anyway. Why not just persist the look-back data along with the entity instead of putting it out on the edge? Now we don't have to worry about deleting anything. An ordered sequence. So events and commands and whatever come in any order that they want to. And there's even latency on one of them. Event number 2. What do? We simply keep the fact that step 1 has been completed, step 3 has been completed, but step 2 has not been completed. And eventually what will happen? Either the event will arrive that will cause step 2 to happen, and now we can carry out the entire completion of the operation, which says, in essence, a mini process has completed, and now something more significant happens. Instead of, worrying about that, what we know is that that operation or this event will eventually arrive or it won't in time. So if it arrives in time, we complete. If it doesn't, we have a timeout. We then ask the domain expert or experts, what do we do about a timeout? What happens if this fails? It's a business problem that we have to understand that in this environment, we are dealing with this. What are we going to do about that situation if we have a timeout? Well, we have to do this. Okay, we build actually a business policy around it just to make it technically work? No. to satisfy the customer, to make the customer happy, to make their experience better. We're going to care for them. We think about the customer or whatever is involved in this, the end, the person or persons or group or whoever that we are trying to satisfy, and we make this a very satisfying situation for them, whether it works or not. Okay, they're going to be a little less happy, So how many of you have ordered a book from Amazon and it says, "Thank you for your order," right? 3 hours later, you get an email that says, "We're out of stock," right? What do they tell you? Okay, you got a couple choices. Would you like to cancel that part of the order? Would you like to cancel the whole order? Or would you like to go ahead and ship the current available items and we'll ship the other one when it's available? What do you usually do? I'll take it when it's available. Is it really so important that you're going to throw everything else out? No. So there is a satisfactory conclusion to the fact that Amazon deals with uncertainty all the time. We'd like to think that when I click on, checkout, that book is mine. It may not be in reality, right? Now, what if we receive, okay, same problem. The point is here that we only want to emit one event at the end of this mini process completing. When 1, 2, and 3 are completely satisfied, now the big conclusion happens. We may have little conclusions in between, capturing the fact that 1 and 3 did happen, but finally when they all happen, then there's some satisfaction. You can do this with, okay, where's the closest warehouse, right? We're going to look for all, we're going to wait for all incoming events that say, right, okay, this warehouse has it, this warehouse has it, and this warehouse has it, and we have some kind of metric or measurement that says, okay, this one's the closest. That doesn't mean 0.3 miles or kilometers, it just means 0.3 something, right? But it's closest. So we order from that warehouse. Or, which is the fastest? Okay, we don't care which is the closest. We want this to ship now. So we take the first one that has the product available, for example. And then sometimes we get into more complex processes where it's multi-step, and the multi-step processes are handled by a process manager. Actually, the process manager is sort of the opposite of an aggregate. It's still an aggregate, but it sees events, it reacts to events, and emits commands, right? Whereas an aggregate typically is receiving commands and emits events. The process manager says, oh, this happened, what needs to happen next? And it could happen in parallel. And it's tracking, the order that things are completed and finally completed and so forth. It's doing the same thing that we were doing back here, right? It's just more complex. More things can happen, right? So let's see what time we have here. Okay. Let me just show you a Java example. Okay. So here's that proposal that I was talking about, and I just want to make a point with fluent language in your code, right? So we have a proposal. This is where a client will use this P2P system. They'll go into a matching system, and they will propose a job. And part of that proposal will probably be that they're typing in some kind of job data that needs to be done, like windows, and then washing, and inside out, right? And extra tall windows, and things like that. And as they're filling in these keywords, we're constantly, saying, okay, well, here's a fair price for that, but they have the opportunity to override, and all these things are going on in the matching context, right? So we're back here in matching, But eventually, that client is going to click submit, right? They want to submit the proposal. That is actually our ubiquitous language. So what does our code look like? We have a method on proposal named submit for. It returns a new proposal, and we literally read in the code, in the client code, proposal submit for client expectations. Now, is that better than like 15, property setters? Can you reason about that, right? Of course. Now, after we have a proposal that's submitted, look at what happens down here. In our constructor, right, we're eventually getting to our constructor, and what are we doing? We're emitting a new domain event named proposal submitted. And that's just basically what happens when a proposal is submitted. We apply or emit an event, and that event that is emitted will then go, right, to pricing and scheduling. Well, it'll go everywhere potentially, but only whoever's interested in it cares, or has the permission to read it cares. Okay? Now what happens? Pricing may come back and say, so price proposal submitted, and it may come back and say pricing denied or pricing approved as events. Explicit, no guessing. It's not just pricing did something, and then you got to look inside to find out, well, was it approved or was it, denied? No. The name itself tells you what happened, right? So that's the result of this. Well, when that happens, what do? On proposal, we have a deny pricing, and we have a deny scheduling, and we have a verify pricing and a verify scheduling. You know where the uncertainty of duplicate delivery is handled? You can actually use if statements. If not proposal was scheduling verified, then apply this new event, scheduling verified, right? If not pricing verified, right? That's it. We're deduplicating right there, okay? It also, there's an implication here that we don't know what the order is that these will return in. Okay, so what do we have to deal with that? In addition to our ID, our client, and expectations, we have a progress. And our progress is a simple value object, right? And our value object starts off with none progress, no progress at all. And as things happen, the proposal simply, right, relays, okay, well, it's a little bit difficult to see here because this is an event-sourced model, which means that everything that happens, I'm emitting an event, but I'm only emitting it if I know it should be emitted. But then down here, we have some methods that say, okay, when the proposal was submitted, I'm going to mutate my state like this. Or when pricing was denied, I'm going to mutate my state like this, right? So it's a separation between what happened and what that does to my internals. Anyway, as we're going through these steps, and if pricing is denied, I use my progress and a side effect-free behavior that will not change this progress state, but I will ask for the progress that I had along with a denied for pricing, right? Or along with a verified for pricing, along with denied for scheduling or verified for scheduling, right? And then I have the ability to simply ask, right? Well, it's easier to see here. When the progress transitions, I can simply ask the proposal, are you acceptable or are you unacceptable? if you're, and you can also ask, was it completed, right? So all of these things basically happen to deal with the fact that you don't know when things will happen, and you don't know the order in which they will happen, but it doesn't matter. We simply model for it. Now, is this complex code? Can somebody just tell me, how complex is this? That's why I said, I'm going to show you stuff that may be disappointing because you thought you were going to come in here and see some magic. And I'm like, no, it's not magic at all. It is simple. Think in terms of the simplest thing that could possibly work. And it's explicit. It's a ubiquitous language. It's what the business thinks about. Was there a progress originally understood when we were talking about proposal? No. No, because we weren't dealing with the uncertainty. But as soon as we understand that there's uncertainty, then we raise the question that asks for the answer to the unknown unknown that says, you know what I just realized is, what if all these things start happening out of order and simultaneously and duplicates and whatever, what do we do about it? Oh, what if we just had a progress? We have a progress and it tells us where we are. And we always know where we are. We know what has happened and what still needs to happen. And so we add progress to our ubiquitous language, right? And we have some kind of a spec concept, and all the spec is an enum that says, well, I know that I can be submitted, I can be also denied for pricing. All of these situations can exist, and, right? And now we just have these one-line methods that just manage that uncertainty for us. And ultimately, right, they're all calling this with new spec, which is 3 lines of code. Isn't this beautiful? It's elegant. And it's so simple. Why do we go through? Our industry is so addicted to complexity. I really think, people, I talk to developers all the time. It's like they brag about how complex their systems are. And I can see through it in an instant, and I can look at it, I can hear what they're saying, and I can say, well, I don't want to be offensive to people, but look, this is way simpler, and people can actually understand. I can bring a domain expert in here to this code, and I can walk through it with them, and they can understand this. I can say, is it true that a progress is unacceptable when it's been submitted and it's pricing denied or it's scheduling denied? Is that correct? Yes, that's correct. It reads like a human can understand it because they can, right? So, I hope I didn't disappoint you too much in how easy this is, and I did go 4 minutes over time, but think about this. Try to use these concepts, these ideas, and you're going to find that delivering software, complex software, becomes much, much more simple when you boil it all down to a language and you solve the uncertainty in the domain model. All right, so thank you for attending.